I'm happy to say that we have a new corporate sponsor. So I was in the Walmart that's off I-35 the other day, and I took this picture because I thought the advertising was just amazing. This is for Depends underwear, and so I contacted the CEO of Depends, and he was happy to sponsor our class. And just look at the smiles on these faces. They look so happy. These guys, it looks like they just had the best sleepover ever. And these other guys are like, no, we had the best sleepover ever. And so the advertising here is on point. And I like to try out the products before I endorse. And I have to say that these are so comfortable, so absorbent. As you can see here, they wick away liquids and turn it into a gel. And the gel just feels incredible. So pick up a pack of these because I know some of you might go out and party a little hard on the weekend, and you might not want to get up in the middle of the night. And so, like I said, pick up a pack, and then if someone ever asks you if you wear boxers or briefs, you can say depends. So how do we take derivatives of functions like these functions? So notice we have, for example, the square root of x to the fourth plus 7x squared plus 3, or natural log of x squared plus 1, or 2x plus 9 to the fifth power. Now, each of these functions is an example of a composition of simpler functions. So for example, this one right here, we have an inside function, x to the fourth plus 7x squared plus 3, and we have an outside function, the square root function, or the square root of x. Same thing here. This f down here can be considered the composition of an inside function, x squared plus 1, with an outside function, natural log or natural log of x. Okay, right here we have 2x plus 9 is the inside function. The outside function would be x to the fifth. Okay, whatever your inside function is, you kind of think of it as just one big x, and your outside function is what's left. It would be x to the fifth. So how do we take derivatives of compositions of functions? Well, we're going to do it using something called the chain rule. So the chain rule says if f of x is g of u of x, now this does not mean g times u. Okay, g and u are going to be functions. This is g of u of x. So we're putting the function u, or u of x, inside the function g. How do we take the derivative of this composition of functions? Well, the derivative, f prime, is going to be g prime of u of x times u prime of x. Okay, now that probably looks pretty confusing. Okay, what does that mean? Well, the way I think about it is like this. I think of the u as like the inside function and the g is the outside function. The way to take the derivative of this composition is to do the derivative of the outside function, right, g prime, but not g prime of x. We apply it at u of x. We don't do g prime of x, we do g prime of u of x. So the derivative of the outside function applied at the inside function, then times the derivative of the inside function, the derivative of the u. Okay, so let's do an example. Again, this probably seems confusing until you see some examples. So we have f of x is 2x plus 9 to the fifth. Now in the notation up here, our u of x would be the 2x plus 9. U of x would be 2x plus 9. And what would the g of x be? Well, the g of x would be x to the fifth. Okay, you think of the whole inside function as just one big x. What's left is x to the fifth. That's the outside function. So we could think of this as a composition of an inside function and an outside function. So the way we take the derivative is f prime of x is going to be the derivative of the outside function. Okay, the derivative of the g. What's the derivative of the x to the fifth? Well, it's 5x to the fourth. But instead of putting 5x to the fourth, I'm going to put 5 times the inside function to the fourth. Remember, we don't apply it at x, we apply it at the inside function. So 5 times 2x plus 9 to the fourth, and then times the derivative of the inside function. In this case, the derivative is just 2. So that is our final answer. Now we could simplify this a little bit. The 5 times 2 is actually 10, and we could write this as 10 times 2x plus 9 to the fourth power, and leave our answer like this. Okay, so notice we took a derivative of a composition of functions. Let's do another example. Here we have the square root of x to the fourth plus 7x squared plus 3. Whenever we see a root and we're doing a derivative, we want to rewrite it so that it doesn't have a root, so it has an exponent instead. Okay, so we have this inside part here raised to the 1/2 power. Now again, we have an inside function, x to the fourth plus 7x squared plus 3, and the outside function in this case is just x to the 1/2 power, or the square root of x. So how do we take the derivative? Well, the derivative of the outside function, the derivative of x to the 1/2 would be 1/2 x to the minus 1/2. But instead of putting 1/2 x to the minus 1/2, we're going to put 1/2 times the inside function to the minus 1/2. And then in the end, we multiply by the derivative of the inside function. The derivative of x to the fourth is 4x cubed. The derivative of 7x squared is 14x. The derivative of 3 is 0. And so this is our final answer. Now, so far, I haven't given you any reason to believe that the chain rule is actually true. I just gave you the rule. So let's do a problem where we could do it using the chain rule and we could do it without using the chain rule. And let's see if we get the same answer. So suppose we have f of x is 5x plus 1 squared. How could we find f prime of x? Well, let's do it two different ways. First of all, without using the chain rule. And then second, using the chain rule. And let's check to see, do we get the same answer? So how could we do this problem without using the chain rule? Well, what we could do is just rewrite this as 5x plus 1 times 5x plus 1. That's what 5x plus 1 squared means. Okay, and then let's simplify this. Let's FOIL this out. 5x times 5x would be 25x squared. We're going to get a 5x from the inside two terms, right? 5x times 1. And another 5x from the outside two terms, 5x times 1. So that'll give us a total of 10x. And then finally plus 1, right? 1 times 1. Okay, so notice I didn't do any calculus there. I didn't do any derivatives. I'm just rewriting 5x plus 1 squared as 5x plus 1 times itself, and we FOILed it out. Now, what is the derivative? Well, the derivative is going to be 50x plus 10. Okay, the derivative of this polynomial is just 50x plus 10. So again, what we did is just FOILed this out, and then so we simplified it ahead of time and then took the derivative. Now, what would we get if we used the chain rule? Well, notice we have an inside function being squared. We have something squared. So what is the derivative of this? Well, the derivative of the outside function, okay, the derivative of x squared would just be 2x, or 2x to the 1. So the derivative of a function squared is going to be 2 times the function to the 1. We don't need to put to the 1 power, but then times the derivative of the inside function. Okay, and notice if we simplify this, 2 times 5 is 10, that's 10 times 5x plus 1. If we distribute the 10, we're going to get 50x plus 10. And notice that's the same answer that we had before. Okay, now you might think, well, why do we need the chain rule? If we could just do it this way, why do we need the chain rule? Well, imagine if we had a higher power than 2 here. What if this were raised to the 7th power? Well, I wouldn't want to try to FOIL out 5x plus 1 times 5x plus 1 times 5x plus 1 7 times. That'd be a big pain. But to do the chain rule, it'd be pretty simple. If you had this to the 7th power, the answer would just be 7 times this to the 6th power, and then times the derivative of that, right? The 5 there. So again, the chain rule could handle that no problem, whereas trying to FOIL it out would be a big mess. But it is always comforting to know that you can do a problem like this in two different ways, and you do end up getting the same answer. So the chain rule really did work. Okay, let's do another example. How do we take the derivative of natural log of x squared plus 1? Now, we can't take the 2 up front. We can't break this apart. Like, this is not the same as natural log of x squared plus natural log of 1, right? There's no nice way to simplify this function ahead of time. But we can think of it as a composition of functions. Oh, and by the way, this is not natural log of x times x squared plus 1, right? This is not a product here. We're not multiplying, so we're not going to use the product rule here. What we have is a composition. We have an inside function, x squared plus 1, and an outside function, natural log of x. Okay, again, think of the inside function as just one big x. The outside function is natural log of x. So the chain rule tells you the way you take the derivative of a composition of functions is to do the derivative of the outside function. So what's the derivative of natural log of x? It's 1 over x. But instead of putting 1 over x, we're going to put 1 over the inside function. And then finally, we multiply by the derivative of the inside function out here. And this is perfectly fine to leave your answer like this. You might also want to just rewrite it as a single fraction here and just write it as 2x over x squared plus 1. Okay, so we use the chain rule. Now, what about this one? K of x equals e to the 5x cubed minus 6x. Well, notice, again, this is a composition. We have an inside function, 5x cubed minus 6x. And the outside function, we have e to that thing, right? We have e to the x is the outside function. Okay, so how do we take the derivative of a composition? Well, again, we take the derivative of the outside function. The outside function is just e to the x. And the derivative of e to the x is just e to the x. But again, instead of putting e to the x, we have to put e to the inside function. And then in the end, we multiply by the derivative of the inside function. Okay, and that is our final answer. Now, you could put this part out in front of the e, but the way you take the derivative of e to the something is just going to be e to the something, and then times the derivative of the something. In fact, the chain rule tells us a couple things. It tells us that if the derivative of natural log of x is 1 over x, which we know, then the derivative of natural log of something, right, of some u of x would be 1 over that something, then times the derivative of the something. So again, since the derivative of natural log of x is 1 over x, the derivative of natural log of u of x is going to be 1 over u of x, but then times the derivative of the u of x. So as another example, how would we take the derivative of natural log of something? Okay, well, the derivative of natural log of x was 1 over x. The derivative of natural log of something is going to be 1 over the something, but then times the derivative of the something, which would be 5x to the fourth plus 3. And that's our answer. And again, you could write it as a single fraction, 5x to the fourth plus 3 over x to the fifth plus 3x plus 1. Okay, so whenever you have natural log of something, the derivative is just going to be 1 over the something, and then times the derivative of the something. Now, the chain rule also tells us that since the derivative of e to the x is e to the x, and we know that, right? The derivative of e to the x is e to the x. The derivative of e to the something, to some function of x, some u of x, will be e to the something, but then times the derivative of the something. So again, if the derivative of e to the x is e to the x, the chain rule tells us the derivative of e to the something is going to be e to the something, but then times the derivative of the something. So as a quick example, if g of x is e to the 5x cubed, g prime of x is going to be e to the 5x cubed, but then times 15x squared. Or you could rewrite it as 15x squared times e to the 5x cubed. So again, the fact that the derivative of e to the x is e to the x means the derivative of e to the something is e to the something, but then times the derivative of the something. That's what the chain rule tells us. And last of all, we have kind of a generalized power rule here. If you have the derivative of x to the n, we know the derivative is n times x to the n minus 1. What about if we have some function to the n, some u of x to the nth power? Well, the derivative will be n times that something to the n minus 1, and then times the derivative of the something. As a quick example here, we have something to the 7th power. So what is the derivative of something to the 7th power? Well, it'll be 7 times that something to the 6th power, and then times the derivative of the something. Okay, so if you have something to the 7th, the derivative would be 7 times the something to the 6th times the derivative of the something. And there's various ways maybe you could simplify this, but let's just leave our answer like that. Now, what about if we had just x to the 7th? I told you the derivative of something to the 7th was 7 times the something to the 6th times the derivative of the something. What if our something was just x? What would the derivative be? Well, the derivative of something to the 7th power is 7 times the something to the 6th power, but then isn't it times the derivative of the something? But what's the derivative of x? It's just 1. And so our answer is really just 7x to the 6th, just like we thought it was, right? We've always known here that the derivative of x to the 7th was going to be 7x to the 6th. But you could think of your inside function as just being x here, right? You have x to the 7th. The derivative would be 7 times the x to the 6th, but then times the derivative of the x. But whenever the inside function is just x, the derivative out here will just be 1, so you don't even really have to use the chain rule. Now let's look at two more examples real quickly here where we have to combine some derivative rules. So notice we have x cubed times e to the 4x plus 1. We actually have a product of functions. We have a first function, x cubed, times another function, e to the 4x plus 1. So how do we take the derivative? Well, to take the derivative, we're going to have to use the product rule. We can't just do the derivative of the first function times the derivative of the second, right? We have to use the product rule. So what's y prime, or dy dx? Well, it will be the first function, x cubed, times the derivative of the second function. Now, what's the derivative of e to the 4x plus 1? Well, it's going to be e to the 4x plus 1 times 4. Okay, we had to use the chain rule there, right? So we have the first function times the derivative of the second, that goes there, plus the second function times the derivative of the first. The derivative of x cubed is 3x squared. So notice the overarching rule that we're using here is the product rule. We have a product of two functions, but in the process of using the product rule, we had to take the derivative of this second function, and the way you take the derivative of e to the 4x plus 1 is to use the chain rule. We get this here. So we combined the product rule and the quotient rule. Now we could simplify our answer a little bit. In fact, if you're to see this in the back of a book somewhere and check your answer or check an answer on MyMathLab, it might be simplified. And so let's actually simplify this. Let's bring the 4 out front here and write this as 4x cubed times e to the 4x plus 1. And over here, let's write the 3x squared first and write this as 3x squared times e to the 4x plus 1. So this would be another way to write your answer. In fact, notice we really have two terms. We have this term here and this term here, and they have an e to the 4x plus 1 in common. So you could actually factor out the e to the 4x plus 1 and write it like this: e to the 4x plus 1 times 4x cubed plus 3x squared. Okay, and write your answer like this. And for our last example, notice we have a quotient of two functions. So we can't just do the derivative of the top divided by the derivative of the bottom. We have to use the quotient rule. Remember, the quotient rule is low d high minus high d low all over low squared. And notice also that in the process of using the quotient rule, we're going to have to do a d high. And how do we do the derivative of the top? Well, we use the chain rule. Okay, so low d high minus high d low all over low squared. So let's write f prime of x equals. Now, I like to put the low squared part first. That's real easy. X to the fourth plus 3x, quantity squared. There's the low squared. Now let's do low x to the fourth plus 3x. Make sure to put it in parentheses. Times d high. Now what's the derivative of natural log of something? Well, it'll be 1 over the something. And then times the derivative of the something, which would be 5. Okay, so there's the low. And this whole thing right here is the d high minus high times d low. And what's the derivative of the bottom? Well, it'd be 4x cubed plus 3. Now, if you write it like this, you get it wrong, right? Because we need to put parentheses around here. It's the natural log of 5x plus 1 is not just being multiplied by the 4x cubed. It's multiplied by the whole thing, 4x cubed plus 3. So again, notice we used the quotient rule in conjunction with the chain rule, right? We notice, oh, we have a quotient here. So our overarching rule that we're going to use is the quotient rule, right? We're going to do low d high minus high d low all over low squared. But in the process of doing that, we have to take the derivative of the top here. And the way you take the d high, the derivative of the top, is to use the chain rule. Now, I thought of one more example where we could take the derivative in two different ways. We could take the derivative using the chain rule or not using the chain rule. So how could we take the derivative of natural log of x to the fourth? Well, we've talked about this in a previous module. What you can actually do is simplify this ahead of time. This 4 can come out front. So we could rewrite this as 4 times natural log of x. And now we know how to take the derivative, right? The derivative of 4 times natural log of x is going to be 4 times 1 over x, okay, which is just 4 over x. I remember the derivative of a constant times a function is just the constant times the derivative of the function. By the way, you could use the product rule. You could do the derivative of this times this is this times the derivative of this plus this times the derivative of this, but the derivative of that constant is just 0. So it ends up just being 4 times the derivative of this. So your answer is just 4 over x, but you could do this using the chain rule. I think that way probably is the easier way, but you could take the derivative using the chain rule. So another way to do this would be to say, well, the derivative of natural log of something is just 1 over the something, but then times the derivative of the something. Okay, so what we get is 4x cubed over x to the fourth, but notice x to the fourth over, or x cubed over x to the fourth is really just 1 over x. So the answer here is just 4 over x. And notice we get the same answer in both cases. So here what we did was we simplified ahead of time. We brought the 4 out front and then took the derivative, just like we did in previous modules. Another way to do it would be, well, what's the derivative of natural log of something? Well, the chain rule tells you the derivative of natural log of something is 1 over the something, but then times the derivative of the something. And when we rewrite this, we get the 3 x's on the top. We'll cancel 3 of the x's on the bottom. We're left with 1 x there, and we still have the 4 on the top. So we get 4 over x in both cases. So again, it's kind of reassuring to know that the chain rule actually works.